Okay, before we get started today, I want to encourage everyone to go into 101 and 103 and look at your grade book and look for any zeros. If there's a zero there, that means I don't have anything from you. In other words, you didn't submit anything for that assignment. Otherwise, there'll be a grade other than zero there. Let's see. Let me close the door. I found a review document. I'm not sure if it's in Brightspace. I think it is, but it looks like any other exam. You'll notice at the top there are 120 basis points and 80 bonus points. That's a lot. I'm going to try to go through all of them. And we've got today and Thursday to get through all of these. And that'll give you a thorough review for the final. Okay. So let's scroll down a little bit and get some of this stuff out of my way. There we go. Some of these are going to be quick and easy. We'll just knock them out really fast. Which of the following is an example of a quantitative observation? Remember, quantitative versus qualitative. Quantitative implies measurement. You have a number and a unit of measure. Qualitative is more generalized. It's a descriptive term like color or size or relative colors, sizes, relative characteristics of two or more objects. That's qualitative. So quantitative requires a measurement. And out of those A through E, the only one that's quantitative is temperature. That D is temperature. The rest are qualitative. So here we're talking about the difference between precision and accuracy. Remember, accuracy is relative to an accepted value. Sometimes it's a true value, but most often it's just an accepted value. How close is it to the accepted value? Precision, on the other hand, is grouping. So they're either tightly grouped, close to the same measurements for multiple measurements, or they're very far apart. So the question here is, which one of these represents a picture showing high precision? That is grouping. And you'll see that Roman numeral 2 and Roman numeral 3 both have very tight groups. So 2 and 3 means E. Now, if we were looking at accuracy, the only one that would show accuracy is number 3, or Roman numeral 3. 2 is too far away from the bullseye, and the average values for the one in Roman numeral 1 don't put it anywhere near the bullseye. I'm not sure why that one has S. Let's figure that one out, and then I'll change that one to the correct value. The amount of uncertainty in a measured quantity is determined by. Okay. When a measurement is being made, you've got two factors. You've got a device of some kind. It could be very simple, like a ruler, a meter stick, a balance. It could be something very complex and very expensive, like a spectrometer of some kind. But you also have an operator, someone who is required to turn it on, calibrate it, actually make the measurement. The skill of both the operator and the accuracy of the instrument itself are two variables that go together to determine whether a quantity measured is accurate or not. So this uncertainty that we're trying to get a handle on is determined by both the skill of the observer and the limitations of the instrument, which would be A. So let me change that to the correct answer. All right. 4. The boiling of water is, all right, look at your answers to see what we're getting at. Physical change, chemical change. Right? The boiling of water, does the identity of the substance change? No, it doesn't. So this is a physical change. Right? That's a physical change, but there's more to the statements. Why is it a physical change? Well, A says it's a physical change because the water disappears. The water doesn't disappear. The water changes from a liquid to a gas. The second one says physical change because the water is chemically the same as the liquid. That is true. And the rest say chemical change, so they don't count. So B is your answer. Okay, number 5. A solution is also called a, right? Solution is another term for a mixture. And a mixture is a combination of two or more pure substances that do not change their identity in the process. So when we make a solution of two or more substances, we make a mixture that must be homogeneous to be a solution. So that's A. Six, which of the following has a different value on the moon compared to the Earth? Right? What is mass? A mass is a measure of the amount of a substance. It's independent of any other factors as long as you're not relativistic, right? If you're going close to the speed of light, then all bets are off. But under normal circumstances, or if you're close to a black hole, then things get kind of squirrely. But otherwise, mass is constant no matter where you are, right? So it's going to be the same on the moon as it is on Earth. Time, same thing for time. As long as you're not relativistic, time is a constant. Time is the same no matter where you are. Weight. What is weight? Whereas mass is a measure, let's see, a measure of substance. Weight is a force. And we know forces can change. In the case of the Earth versus the moon, the force is being applied based upon gravity. Gravity on Earth is greater than it is on the moon. So two same equal masses on Earth and moon will have different weights because they're under the influence of different gravitational fields. D, moles. Moles is constant no matter where you are. Moles is just the numbers of things, right? So C is the one that's different, depending on the gravitational field. All right, 7. All the following are true except. So we're looking at ions, ions, ions. Okay, how do you get an ion? If you start with a neutral atom, right, you have numbers of protons and you have numbers of electrons, and these are equal. So how do you turn that into an ion? You can't remove protons or you can't add protons, otherwise you got a different element. So the only way to make an ion is to change the number of electrons. Right? So ions are formed by changing, well, which one is, okay, we're looking for the exception, pardon me, the exception. So A should be true. Ions are formed by adding electrons to a neutral atom. That's one way to form an ion. You can also form an ion by removing electrons from a neutral atom. That's A and C. B, ions are formed by changing the number of protons. No, no way. Cannot happen, will not happen. An ion has a positive or a negative charge. That's also true. And the last one, metals tend to form positive ions. Is that true? Yeah. Metals want to give up their electrons. So they're all true except for B. Okay, 8. All of the following are characteristics of metals except. Well, let's see. A, B, C, D, and E. So A says metals are good conductors of heat. Is that true? Oh, yeah. That's true. How about metals are malleable? Right? Pure metals are very malleable. You can even take pure iron, 100% iron or close to 100% iron. You can scratch it with your fingernail. Ductile. What does ductile mean? It's true. Ductile means it can be stretched into a thin wire without breaking. And often lustrous. Lustrous means they're shiny. They're only shiny when they're polished. Metals that are not polished may not be lustrous, but that's why we say often lustrous. And E, tend to gain electrons in chemical reactions? No. They tend to lose electrons in chemical reactions. All right. So what's number 9? Which of the following is paired incorrectly? All right. Each one of these is acid or base and could be strong, it could be weak. So the first one is comparing H2SO4, calling it a strong acid. That's true. Sulfuric acid is strong. And we have to assume that all of these are in aqueous solution. HNO3, weak acid? No. Nitric acid is strong. Right? So since we have only single choices for this question, we found our answer. Barium hydroxide is a strong base. That's true. Hydrochloric acid is a strong acid. That's true. And NH3, ammonia, is a weak base. So what do we mean by acid base? The Bronsted-Lowry definition means that if it's a weak base, it does not have a strong attraction for hydrogen ions. That makes it a weak base. All right, number 10. Which of the following is incorrectly paired? All right. So we're pairing symbols, right? So the wavelength, is that lambda wavelength? Yes, it is. How about frequency? That's the Greek letter nu. That's frequency. Yes, it is. Speed of light. We typically say a small c for the speed of light. That's true. Hertz. Hertz is reciprocal seconds. In other words, hertz is a measure of my mind's gone blank. Frequency. Yeah. Frequency. Hertz is frequency. In other words, it's how many wave crests pass a single point in 1 second. That's hertz. And then X-rays, shortest wavelength. Incorrectly paired. X-rays have the shortest wavelength. You know what? Incorrectly paired. X-ray shortest wavelength. X-ray shortest wavelength. They're all true. X-rays have the highest frequency, which means the shortest wavelength. Okay, the only way that this could be incorrectly paired. Oh, no, my mistake. That's not the shortest wavelength. It does have a short wavelength, but the shortest wavelength is gamma ray. Right, so E is false. It does not have the shortest wavelength. Gamma rays have the shortest wavelength. All right, and number 11. Consider the following portion of an energy level diagram for hydrogen. For which of the following transitions does the light emitted have the longest wavelength? Right. Remember, the longest wavelength equals the lowest energy. And how do we get the lowest energy in an electron transition? The lowest energy is the shortest jump. So if we draw a little model and we say, this is principal quantum 1 or first energy level, the second energy level might be here, the third might be there, and the fourth would be even closer than that. So the shortest jump is, in this model, it's going to be from 4 to 3. Right? 4 to 3 will give you the shortest jump. Right? And that's A. All right, 12. Which of the following statements best describes the Heisenberg uncertainty principle? Remember, the Heisenberg uncertainty principle in words simply says that you cannot know with accuracy both the position and the velocity. I think it's termed, instead of velocity, it's momentum. But if the mass is constant, then we're talking about velocity. You can't know both of those with any accuracy. for an electron. A says the exact position of an electron is always uncertain. No. It's just if we pin it down, if we find out exactly where it is, we don't know how fast it's moving. And that also translates into energy. We don't know what the energy is. B says the velocities of a particle can only be estimated. No, we can identify the velocity. Problem is, if we do that, we don't know where it is. So C says it's impossible to accurately know both the exact location and the momentum of a particle. That's momentum. Momentum, this Greek letter rho, is equal to mass times velocity. So if we're talking about an electron, then the mass is going to be the same, no matter what you do, measure it. So we're talking about velocity. But the expression in Heisenberg's math is in terms of momentum. So C is correct. C is the correct answer. Number 13. All right, which of the following is an incorrect designation for an atomic orbital? All right, now we're talking about the configurations for an atomic, for any atom. So remember, we have the principal quantum number. We have the let's see, principal quantum number can be 1, 2, 3 on up. L, or the angular momentum quantum number, can be 0, 1 on up to n minus 1. Okay. Then the magnetic quantum number can be minus L to 0 plus L. And then the spin quantum number can be plus 1/2 or minus 1. Okay. So if we have n equals 1, let's see, A, B, C, D, E. If n equals 1, can L, well, we also have to, let's see, let's put in here 2 and 3. This is S, this is P, this is D, and this is F. Okay. So if n is equal to 1, then n minus 1 is 0. Yes, it can be 1s. L equals 0 or S. That's true. 3D. If n equals 3, what can L equal to? If this is 3, then we can go up to L equals 2. D, that's correct. It will work. That's 2 or D. That's true. How about C? 1P. If n equals 1, can L equal P? No. If n equals 1, it can only be 0. So that's wrong. C is wrong. Cannot be. If we keep going to n equals what? 4, then we could have L equals 3. That's true. That's F. And E, 6s. Oh yeah. N can be any number. It always has an s orbital. Okay, so the wrong one is C. Okay, 14. Yep, 14. Which of the following was not an elemental property usually predicted by Mendeleev for as yet unknown elements? So Mendeleev predicted properties for unknown elements. He predicted the expected mass of the element, the atomic mass. He predicted the density. He even predicted boiling points. And he predicted the formation of oxides. Most elements, naturally occurring elements, especially if they're metals, but very often if they're non-metals, are combinations with oxygen. That's why oxygen is the most common by mass element on the Earth's surface, either in the crust or in the atmosphere or in the lakes and oceans. One thing that Mendeleev did not have access to was electron configuration that we just discussed in the past problem. So A is the one that he had no idea about. It was too early for that. (15) Which of the following atoms has 3 electrons in p orbitals in the valence shell? All right. So A, B, C, D, and E. So what do we got? Oh, E is none of these. And we're looking for 3 electrons in the p orbital. 3 electrons in valence p orbital. Okay. So we've got barium, gallium, vanadium, and bismuth. Okay. You can write out the electronic configuration. That's fine. It'll take extra time. What we want to know is p orbitals that have 3 electrons in them. If you know your periodic table, you know how to use the periodic table, then you can determine that simply by looking at where the element's located. So barium is in period, well, it's period 6, but it's group 2. Group 2 has no p orbitals that are unfilled, so it can't be barium. Gallium has 1 p orbital. It's group 1, 2, 3. Well, that's the old system. Group 2, this will be group 13. It only has 1 p electron. Well, actually, it's not 1 p, it's 4 p. It's 4p1, based upon where it is in the periodic table. Vanadium has filled orbitals. Its valence shell is 4s2. It has no p orbitals. It has a 3d. 3? Right? How about bismuth? Bismuth is in group 15. And at that location, bismuth has 6s2, 5d10, and 6p3. There it is. And that's based simply upon knowing the periodic table, how it's structured, and how to read it in terms of electronic structure. So bismuth is our answer. All right, 16. The force between 2 bodies having identical electric charges is repulsion. It's pure and simple. That's it. B says repulsion if the charges are negative and attraction if they're positive. No. Opposite charges attract, same charges repel, always. So A is the only possibility there. 17. Which of the following pairs of compounds can be used to illustrate the law of multiple proportions? Remember, multiple proportions are referred to binary compounds, and like one element and the second element. And then if you compare a homologous series of these elements, then it would be something like this, like that. In other words, the ratio of the second element, if we hold this one constant, the ratio of the second element is whole number multiples. So which ones satisfy that? Well, A can, right? Because it's got chlorine in one, it's not in the other. Zinc oxide and zinc chloride can't work because one has oxygen, the other one's chlorine. C has hydrogen and oxygen and hydrogen and chlorine. That can't work. D has nitrogen, oxygen, and nitrogen, oxygen too. So it would be like this one and this one, right? So there's your answer, D. Number 18. Which among the following represents a set of isotopes? All right. So we've got Roman numeral 1 through 5. What's an isotope? An isotope is a set about two or more nuclei that have the same number of protons and different numbers of neutrons. So where do we go with that? Well, let's see. One has 20 and 20. So one would be 20 here and 40 there. Right, 20 plus 20. Two would have 21 and 19. So this is 21, and 19 would also be 40. 3 would be 22 and 18. And 18 plus that is 40. And Roman numeral 4 is 20 and 22. 20 and 42. So there you have one here and one here. So 1 and 4, those are isotope pairs. And Roman numeral 5, what does it have? 21 and 20. 21, which would be 41. 21, aha. So this one and that one. So we have 1 and 4 is a pair, and 2 and 5 is a pair. That's why D is the answer. "19. Which of the following has 61 neutrons, 47 protons, and 46 electrons? Okay. Neutrons, protons, electrons. Neutrons, protons, electrons. And we got 61, 47, and 46. Okay. We can find out what our element is by that number right there. 47. If we go to 47 on our periodic table, that's silver. It'll be 47 here. And it's missing an electron. If the balance is toward the positive by 1, that makes an ion. And then the value up here would be 47 and 61 is 108. So we're looking for 108, 47 silver. But it's got to be an ion. That's B. Right? E won't get it because E is neutral. B is the correct answer. All right, 20. All the following are in aqueous solutions, okay, which is incorrectly named. How about the first one? H2SO4, is that sulfuric acid? If it's an aqueous solution, yeah, that's sulfuric acid. H2CO3. And remember, if there's an oxygen, you don't start it with hydro. You go to the polyatomic ion part. You find out what that represents. Sulfate, 8's become X, so it's sulfuric. CO3 is carbonate, so 8 becomes X, carbonic acid. That's true. C, PO4 is phosphate, 8 becomes Ic, phosphoric acid. True. D, cyanic acid. There's no oxygen there. So we should start that with hydro. Hydrocyanic acid. That would be the correct name. And HCl is hydrochloric acid. That's true. So D is the bad one. D is not named correctly. '21. Which of the following ions is most likely to form an insoluble sulfate? Okay, in this case, you can go to your, let's see. Go to your solubility chart, which is at the back here. This last one right here. All right, you know how to use that. Cations across the top, anions down the left, and see which matches. Which one forms an insoluble sulfate? Well, sulfide ion and chloride ion would be silly because you don't form a compound with two anions. So it's either potassium, lithium, or calcium, and you look it up in your chart and you find it's calcium. Calcium sulfate is insoluble in water. Okay. Let's see if I got a fresh marker. Yep. Number 22. Okay, a manometer is attached to, oh, I got it covered up. Well, I got it covered up with the answer. Let me go to 22 here and read it. Here it is. No, that's not 22. Uh-oh. I think I'm working from the wrong document. Yeah. In this document, it's 19. And the one I'm showing you here is 22. Okay. So I suspect that there's some in this document that are not going to be in our discussion. My mistake. We'll take them as we get them. Anyway, we're reading a manometer is attached to a sample of gas that occupies a volume of 2.34 liters. So you've got this device, which is 2.34 liter. And the mercury level in the arm of the manometer attached to the gas sample is 24.3 torr lower than that in the arm open to the atmosphere. So if we do like this, that open to the atmosphere. So we've got 1 atmosphere pressure. And this side is 24.3. So we got a level here of mercury and a level here of mercury. And that distance is 24.3 torr difference. Okay. Atmospheric pressure is 1.23 atmosphere. Okay. What's the pressure inside there? Well, first of all, let's qualitatively. Is this pressure higher than atmospheric or lower? It's higher because it's pushing on this hard enough that it can support that extra mass of mercury. What we also need to know is what is pressing down here, 1.23 atmospheres. We need to convert that to torr. 1 atmosphere is 760 torr. So 1.23 times 760 is 934.8 torr. So what do? Do we add this or subtract it? Well, if the pressure in here is greater than outside, we add that. 934.8. Which is 959.1 torr. That's the pressure inside the vessel, or the closest value to it, which is E. Okay. All right, 23 in my version. Let's see. Consider a gas in a 1 liter bulb at standard temperature and pressure that's connected via a valve to another bulb that's initially evacuated. So this is 23. So we got this 1 liter bulb connected by a valve to some other bulb, and we don't know how big it is. This is 1 liter. This is a vacuum. Okay. What occurs when the valve between the two bulbs is open? Oh, answer the following. What is true about the value of delta H? Delta H is what? Well, look at the conditions. 1 liter bulb at standard temperature and pressure. We assume that the temperature is going to stay constant through the whole process. That means this is 0. There is no change in enthalpy in this process. So the answer is B. 24. Let's see. In which group do all the elements have the same number of valence electrons? All right. So we got these groupings of elements. How do we know that they have the same number of valence electrons? They're in the same column in the periodic table. So you look at the periodic table and say phosphorus, sulfur, chlorine. Right? They're in the same period, not the same column. So they don't have the same number of valence electrons. Silver, cadmium, and argon. Well, we can throw that one out because argon is a noble gas, and the other two are definitely not noble gases. How about sodium, calcium, barium? So sodium is an alkali metal, calcium and barium are alkaline earths. So they have different numbers of valence electrons. Phosphorus, arsenic, and selenium. Phosphorus and arsenic have the same number of valence electrons, but selenium is in the next group over, so that throws that one in. So the fact of the matter is, none of them have the same number of valence electrons. Right. 25. The ground state electron configuration of tellurium is, right? We can tell by the answers that were given that we can use the shorthand version. So we start with tellurium. We look up tellurium on the periodic table, and we find that it is 52. So as long as it's neutral, then we can work with all 52 electrons. All right, how do we use an abbreviated form? We go backwards. We find tellurium and go backwards until we get to the next available noble gas. That would be krypton, which has 36 electrons. Okay? So what do we got left? 16. If we go from krypton, then we go down to the next period, which is period 5. And the next one is a 5s. We got 2 electrons for that, right? We got 14 left. Then we go across the transitions, and that's 10 electrons. We got 4 left. Now we go back to 5p, and it's 5p4. So 2, 10, and 4. 5s2, 4d10, and 5p4 is A. Okay? And I did all that from the periodic table. All right, 26. Which of the following bonds would be the most polar without being considered ionic? All right, we're not given actual values, right? So we can't use our rules on where the divisions are. So we have to say, all right, without being ionic. So this is one of those I'm working backwards forwards. If it's not ionic, it means it can't be a metal nonmetal. Right? Magnesium oxide. No, that bond won't fit the conditions. Carbon and oxygen. Okay, possible. Oxygen, oxygen. Okay, that's not ionic. Silicon and oxygen. That's a question. Silicon is a metalloid. So in this case, it may act like a metal, it may act like a nonmetal. We're going to have to keep it for now. Okay. Okay, so if we're saying that these are the possibilities, the next thing you do is say, which following bonds would be the most polar? Which would be the furthest separated on the periodic table? We can't do that one because they're actually equal. Carbon and oxygen, they're 2 apart. In other words, there's 1 in between them. Nitrogen and oxygen, they're 1 apart. They're 1 apart, 1 removed from each other. Silicon oxygen are 1, 2, 3. They're 3 apart. So if this is nonpolar, then that would be the most polar bond without being ionic. Now it's open for debate, but that's the best answer for this question. But it's actually open for debate as to whether the silicon-oxygen bond is ionic or covalent. And we've already discussed that in class, that every bond, except for identical atoms, every bond has a certain ionic character to it. So the most polar is the one that has the most ionic character without being completely ionic. And in this case, the silicon-oxygen bond is our best bet. All right, 27. Which of these is an isoelectronic series? All right, we can use the periodic table to solve this one also. Isoelectronic series. Let's see, E is none of these. Okay. All right, if we're looking at isoelectronic series, generally speaking, they can't all have the same charge because they have to have the same number of electrons. And if they're different elements with the same charge, then that means they don't have the same number of electrons to be in their configuration. So we can throw A out based upon the fact that they're all the same charge. B is possible. If we look at argon, right, that one's out. Argon has 18. So how about potassium with a 1+ charge? How many electrons does it have? Well, potassium is a 19, missing 1, so it's 18. It's good. Calcium is 20, missing 2, so it's 18 also. We got a roll going here. Sulfur is 16, but we're adding 2 more electrons to it, so it's the same as argon. That's it right there. Right? It can't be E because we found one that's true. And you can do the same for C. You can look at that one. D can't be because they're neutral atoms and they all have different numbers of electrons. So D is out for the same reason that A is out. And C, you might have to look at that one and see if it matches. But I'm putting my money on B. All right, 28. Which of the following arrangements is in the correct order of size? Okay, these are all neutral atoms. That's good. Because when you start messing with ions, you're changing the size of the atom drastically. Okay, correct order of size. Let's see, we've got gallium, calcium, potassium, chlorine. Gallium, calcium, potassium, chlorine, and sulfur. What else do we have? Sulfur, chlorine, potassium, calcium, gas. I was looking. That's it. That's all we have. Okay. So if we're going to arrange them in order of size, smallest to largest, which one would be smallest? Based on the periodic table trends, right? What's the trend of size? From left to right, decrease size, right? Because the nuclear charge is getting bigger and shrinking, pulling those electrons in. And from bottom to top, decrease in size. Because the electrons are now occupying, as you go up, occupying orbitals that are closer to the nucleus. So the trend is lower left to upper right. All right, how does that fit in with these? Well, let's see. Where's gallium? Gallium is about right here. Potassium is on the same line. Potassium's over here. Calcium's there. And chlorine is up here, right about there. And sulfur is right here. So from left to right and bottom to top, we should have potassium is smaller than calcium, is smaller than gallium, is smaller than sulfur, is smaller than fluorine. So potassium, calcium, gallium, sulfur, and chlorine would be D. D would be your best answer. 29. Okay, which of the following ionic compounds has the smallest lattice energy? Least favorable to a stable lattice. All right. So what's lattice energy? Lattice energy is the amount of energy that's given up, delta H. The amount of energy that's given up. So it's going to be a negative value. The more negative the value, the larger the energy. And we're going from some cation that's a gas plus an anion that's a gas, and we're making the solid. Okay? So, A, B, C, D, and E. So the first one is lithium fluoride. Uh-oh. Second one's messed up. Let me see. That's a typographical error. Let me see if I can find out what it's supposed to be. Okay. $29. $29. Here we go. No, that's not it either. Okay. Well, the answer is supposed to be B. But you can't form a lattice energy from an element. It must be cesium and something else. Cesium. I'm going to say it's probably cesium fluoride. Sodium chloride, barium oxide, and magnesium oxide. So how do we determine the strength of attraction between an anion and a cation? There are two things. One is charge. What's the charge on the anion and cation? +2, -2 has a greater strength than +1, -1. And distance. What's the distance between the nuclei? Can they get close to one another? Well, lithium is a +1 and -1. Cesium is a +1 and -1. Sodium, barium is 2+ and 2-. Magnesium is 2+ and 2-. And we have to consider size also. Barium is huge. Cesium is huge. Sodium is relatively small. Chlorine is not as small as fluorine. Lithium is very small. Fluorine is very small, but there's only single charges. Right? So this is possibility based on size. Based on charge, it'd be either of these. Magnesium versus oxygen. Oxygen's right next to fluorine. I put my money on this one. I'm not sure why that one is given as the answer. Right? Because it looks to me like magnesium oxide would be the greatest lattice energy. Oh, excuse me. Smallest lattice energy. My mistake. The smallest lattice energy, and by that we probably mean the least negative. smallest, if you actually take it literally, the smallest would be the most negative. Right. But if we go that way, then cesium fluoride would probably be okay. Right. I hope I didn't put that one like that in an exam, because that's very confusing. All right, let's go to 30. It was worth the discussion, even though we kind of danced around the barn several times. Okay, number 30. Let's see. 130. And okay. We got a lab we can use. We go to 350. Which of the following atoms cannot exceed the octet rule in a molecule? All right. Remember, which period allows us to exceed the octet rule? We can't exceed the octet with the second period because we only have access to 2s and 2p orbitals, right? And that's only 8. So we have to be a period 3 or higher. Well, nitrogen is period 2, right? Period 2. The next one, sulfur, phosphorus, iodine, and all can exceed. We know that's not right, because this one cannot exceed. It's period 2. Sulfur is period 3. Yep. Phosphorus is 3. Iodine is 5. So these right here can exceed the octet. The question is, which cannot exceed? And that's this one. I shouldn't have marked that out. That's A. This is the correct answer. That one cannot exceed the octet because it does not have access to d orbitals. All right, 31. Okay. Let's see if I can find that one in here, because I've covered up the text. Here it is. Which of the following has a zero dipole moment? We want dipole equal 0. All right. Remember the two things that you need. If you have polar bonds, if you have nonpolar bonds throughout the molecule and no lone pairs, then the molecule is going to be nonpolar. But if you have polar bonds and each one of these representatives has polar bonds, then the only way that you can come out with a nonpolar molecule is some symmetry. All the bonds, the polar bonds, are pointing in such a way as they cancel each other out. Right? And we've done these several times. So the ones that I know, ammonia, that's polar. Right? NO2. We can draw this one out. N is 5 electrons, and 2 6s are 12s. That's 17 electrons. So we have N, O, O, which means 13 left over. 2, 4, 6, 8, 10, 12, 13. That one's polar also. Right? We have 1, 2, 3 groups around it. So it's going to be a bent molecule. PF5. PF5. Phosphorus is 5, and 7 times 5 is 35. So we have 40 electrons. So we put P 1, 2, 3, 4, 5. 2, 4, 5. That's 30 left over. 2, 4, 6, 8, 10, 12, 16, 18, 20, 22, 24, 26, 28, 30. This is symmetrical. They're no lone pairs. Symmetrical about phosphorus. This is non-polar. That would be a trigonal bipyramid. Okay. We found our culprit, C, phosphorus pentafluoride. SO2 is going to be like water. It's bent. So it's polar. Right. And HCN is like this. Right? So it's polar also. Our nonpolar one is PF5. Let's see. CF. That was not in your copy. I don't see it. So we'll skip 32. I can guess at what it is, what the question, based upon the answer. Which is most polar? All right, that one's kind of a repeat of the last one we did. Let's go on to 33. Which choice has the bonds listed in the order of increasing bond energy? Okay. Increasing bond energy. HF, HCl, and HBr. All right. Bond energy is going to be based upon, well, two things. Difference in electronegativity, size of the charges, and the closeness. So increasing bond energy would be how close can we get for HF, HCl, HF, HCl, and HBr, right? This one's small, this one's medium, this one's large. And they're all the same charge differences, plus and minus. Well, actually, these are covalent compounds. So the bond energy, these are each single bonds. But okay, this is the one that's counterintuitive. The bond energy is related also to the bond length. Now, this is definitely going to be the weakest. That's not the strongest. Okay, this is not the strongest. Right? That's the strongest. Based upon the fact that they're all single bonds, plus the difference in electronegativity draws them close together. But here, the fact that fluorine is a very small molecule, and this is one proton, when that proton gets very close to the fluorine, you're going to get repulsion from the protons. So actually, this one should be, this was the strongest, this is the weakest, and this is intermediate. Right. So that's not the right one. CO, okay. CO is less than COO, is less than COO. Well, I guess it's possible, right? Single, double, triple, right? That's a good guess. And again, when you get the diatomics, the strength of the bond between the chlorides, actually, that's not right. In this case, that's a better approximation. For C, this is the one where you have trouble with the strength of the bond. Let's see. Dichlorine is stronger than dibromine, but dichlorine is stronger than difluorine also. So this one would have, the strongest one would be this, and then probably this one, and then this one. Right, so that's why that one's wrong. And then the nitrogen bond, that one, that's a triple bond. And it's definitely not going to be less than the carbon-carbon bond in C2H4. C2H4 is a double bond. Right? So that can't be it. That disqualifies this one. So our best choice is actually B. Now, I'm not sure where you're going to find a triple bonded O. I guess you could. Say if you put a HCO. You can probably do that. All right. Let's see. 34. Hybridization of the central atom, xenon pentafluoride +1 ion. There we go. So we've got 8 electrons here. We have 5 times 7 is 35, -1 for that positive. Okay. So that should be equal to 42 electrons. Is that right? Yep, 42 electrons. So we have xenon in the middle. 1, 2, 3, 4, 5. Fluorines here. And that's 2, 4, 6, 8, 10 is 32 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So we have 2 electrons left over. They have to go here. Okay. So what's the hybridization of the central atom in this one? Well, it's going to be an octahedron. An octahedral electronic configuration, which means 6 groups. And 6 groups requires 6 hybrid orbitals, right? sp3 only gives you 4. So we need 2 more. D2sp3 is the hybridization for this molecule. Okay, 35. The hybridization of the central atom aluminum in aluminum tribromide. Actually, aluminum bromide is the correct name for that. This is a type 1 compound. Okay, so hybridization. Aluminum has 3 valence electrons. 3 times 7 is 21. Equals 24 electrons. Aluminum, bromine, bromine, bromine. This is probably an ionic compound anyway. Minus 6 equals 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. That's it. So that's 1, 2, 3. This is trigonal planar. And you need 3 lines. So SP2. Okay. Number 36. The hybridization of bromine in bromine trifluoride. So we've got 3, 4 times 7 is 28 electrons, right? And there's no charge, no charge. Okay, so bromine in the middle. We got fluorines around. That's 2, 4, 6, which is 22. 2, 4, 6, 8, 10, 12, 14, 16, 18. 4 electrons. So we have 2 here and 2 here. So that's 1, 2, 3, 4, 5 groups. We need sp3 gives us 4, and we need 1 more. dsp3. Seven. Which molecules have p orbitals that share an electron pair to create pi? Well, notice that each one of these molecules has pi bonds, right? So, which molecules have p orbitals that share? All 3 of them. They all share to form pi bonds. Anytime you have a double or a triple bond, you've got pi orbitals. Pi bonding. 38. Okay, a species has the following molecular orbital configuration. Okay. The substance is paramagnetic or diamagnetic. So remember what we mean by paramagnetic versus diamagnetic. Dio means opposed to. So whatever's diamagnetic is not attracted into a magnetic field, but rejected by the magnetic field. That means no electron, let's see, all electron pairs. There are no free electrons. There are no free radicals. Whereas paramagnetic requires at least one unpaired electron. Okay, so let's look at what we got here. Sigma orbitals can only have 2 electrons. So let's look at the sigmas. Sigma 1s, 1s star, both of those have 2. 2s sigma, it has 2. Sigma 2s star has 2. Now the p's, there's another sigma. 2p is 2. The pi 2p can have 2 levels in it. And this one has 2 electrons. One here and one here. That molecule is paramagnetic because it has 2 unpaired electrons. So the answer is B. Right? Any pi orbital in a molecular orbital description has 2 sublevels. Okay, 39. Which of the following contains the strongest bond? All right, we've looked at this one before. A, B, C, D, and E. So let's see, we're working with N2 minus, N2 2 minus, N2 plus, and N2 2 plus, I think. That's the way it goes. Yes. We're going to work from the neutral molecule first. Right? So nitrogen is going to be, has sp mixing. So if we're working with only the valence electrons, we're going to have a sigma from the 2p, a sigma star from the 2p, then we're going to have a pi 2p, and let's see, no, it's 2s. Sorry, 2s. That's S, that's S. Then a sigma 2s, then a pi star p 2p, and sigma star 2p. Now, that's probably more than we need, but how many valence electrons do we have for N2? Electrons, valence electrons, we have 14. So there's 2 here, 4 there, 2 here, that's 2, 4, 6, 10. We need 4 more right there. They're going to work. Let's see, 6. No, I got something wrong here. Yes. 5. 4. Oh, I got the wrong valence electrons. It's not 14. It's 10. So let's put this one out here, 2p and sigma star 2p. At this point, what's the bond order? The bond order here is 4, 5, 6, 7, 8, minus 2 is 6, divided by 2 is 3. Bond order is 3. Now, if we add an electron, where is it going? The electron is going here. Right? That decreases the bond order by 1/2, right? Because it gives us another, it decreases the numerator by 1 divided by 2 is 1/2. So this is 2.5. If we add another electron here, 2p2, that decreases it to 2. Okay. If we subtract an electron, the electron is being removed from a bonding orbital. So there again, we get sigma 1 2p here. And that decreases it to 2.5. And if we subtract another one, that eliminates this one altogether. And now we're only down to that one as the highest one. And now we're down to 2 again. So any ions that we make from nitrogen decreases its bond order by either adding to an anti-bonding orbital or subtracting from a bonding orbital. So the strongest bond is going to be N2, the neutral dinitrogen molecule. Let's see. I can't read that one. I don't know if I've got it in here. Let me see if I do. No, I don't have it. So we're going to skip number 40. And go to 41. If the Thomson model of the atom had been correct, what was the Thomson model? Thomson's model was the plum pudding model, where the atom had electrons scattered, actual particles scattered, and then the rest of it was just diffuse positive to make up the difference in charge. Whereas the Rutherford model was nuclear model. That means this has all the positive protons in it, and out here are the electrons. And those electrons are negligible mass. Okay, so what happens when you fire alpha particles at them? Well, at this one, there's nothing to slow them down because the positive charge is diffuse and the electrons don't have much mass. So when you fire an alpha particle, when you fire an alpha particle at these things, it comes out and makes a nice bright spot right there. That's it. Whereas if you fire alpha particles at this model, some of them come out here, and then some come out here, all the way around. Because the most of the mass of the atom is right there in the nucleus. Okay, so which one of these satisfies? If the Thomson model of the atom had been correct, Rutherford would have observed alpha particles going through the foil with little or no deflection. That's it. No deflection. But the Thomson model was not true. So we did see deflection. Right. 42. Equal masses in grams of hydrogen, gas, and oxygen are reacted to form water. Which substance is limiting? All right. So if we got hydrogen, gas, and oxygen gas to form water, and we need 2 here and 2 here. Equal masses. So we've got X grams here and X grams here. All right, we can use actual values and it'll work just fine. So let's say we have 32 grams here and 32 grams here. Right. What's the molar mass of oxygen? The molar mass of oxygen is 32. So this is 1 mole. Okay. How about this one? 32 grams, and these are roughly 2 grams per mole. So this is 16 moles. Approximately. All right, if we do it that way, then 1 mole of oxygen requires how many moles of hydrogen? You only need 2 moles of hydrogen to match 1 mole of oxygen. That means we have 14 moles excess. This is excess. This is limiting. Okay, now let's see which one fits. Oxygen gas is limiting? Yes, it is. Hydrogen is not limiting. Water is not limiting because it's a product. Nothing is limiting. This is not a stoichiometric mixture. So we can't say D. And more information? Oh, we got all the information we need. We answered that question right there. It's A. All right. 43. Let's see, a 45-gram sample of metal is heated to 95.2 degrees and then placed in a calorimeter containing 120 grams of water with a specific heat of 4.18 joules per gram degree C at 21.6. The final temperature is 24.5. Which metal was used? All right, out of that selection, what we have to calculate is the specific heat of the metal. All right, remember, everything that happens in Vegas stays in Vegas. All right, so what we're doing here is we're ignoring the heat capacity of the calorimeter. That wasn't given. So we've got to just say this is equal to the heat change for the water plus the heat change for the metal. Okay? All right, so what's the heat change for the water? Well, initial minus final temperature. Final temperature is 24.5 degrees. Initial temperature is 21.6. And the mass of the water is 120 grams. And the specific heat of the water is 4.18 joules per gram degree C. Okay, so the grams cancel, degrees C cancel, leave us with joules. That's good because that's a measure of energy or heat. Okay, then we have for the metal, right? We have the specific heat of the metal. We don't know what is. That's the unknown. And the mass of the metal is 45.9 grams. 45.9 grams. Initial temperature, final temperature, excuse me, is 24.5, same as the water. And the initial temperature is 95.2 degrees. Correct? Yep, 95.2. So now we just have to solve for that unknown. All right, so 24.5 minus 21.6 is 2.9. So 2.9 times 120 times 4.18. And that is 1455 joules. Okay. Then in this one, we have 24.5 minus 95.2. This one is minus 70.7 times 45.9. So it's minus 3245 times the specific heat. Okay, so let's get this one on this side, right? It changes its sign to positive. So now on this side, we have 3245 specific heat of the metal equals 1455 joules. And this value, the grams have already canceled. Let's see, no, we can't cancel. Gram degree C. So this is gram degree C. So if we divide both sides by 3245, we get 1455 joules divided by 3245 grams degree C. Joules per gram degree C, that's specific heat. So our units are agreeing. Let's find out what the value is. Okay, so this is 0.45 joules per gram degree C. 0.45 belongs to which one? Iron. So that's iron. Okay. Let's see. 44. Okay, nitric acid was first prepared 1,200 years ago by heating naturally occurring sodium nitrite with sulfuric acid to produce sodium bisulfate and collecting the vapors of HNO3 produced. Calculate the delta H for the reaction. All right, in this case, well, the reaction's given to us. So we have sodium nitrate solid, plus sulfuric acid, H2SO4, yields sodium bisulfate, solid, plus HNO3 gas. So the information that we're given is heats of formation. So we know that in order to find the delta H under these circumstances, we need to find the sum of the products, or delta H's, minus the sum of the reactants, delta H's. Okay, so sodium bisulfate, let's see if we can find it, is minus 1125.5. Minus 1125.5 kilojoules. And then sulfuric acid. And these are all 1, 1, 1, 1. So we're just multiplying everything by 1. And then H2SO4 is minus 814. Minus 814 kilojoules. Then we're going to subtract sodium bisulfate. I lost somebody, didn't I? No, I guess not. Okay. All right. Then sodium bisulfate is, wait a minute. No, sodium nitrate, excuse me. Sodium nitrate is minus 467.8. Minus 467.8 kilojoules. And then sulfuric acid, H2SO4, is minus 814. Minus 8. Okay. So now that's the hard part, the thinking part. We just need to crunch numbers. So I'm going to do this one first because a negative and a negative is a negative times a negative is a positive. So 467.8 and 814. This is, including that negative, this is a positive 1,281.8. And this one is going to be a negative 1125.5 and 814. Wait a minute. That's not right. HNO3 is 135.1. Bisulfate is correct. Okay. Back 135.1. Now this one is minus 1260.6 plus 1281.8. And I get 21.2 kilojoules. Okay, that's E. Next. Oh, short answer. 45. This would be a good place for me to take a bathroom break. I'll be right back. Okay, let's see. 45. All right, complete the following table. All right, we've got symbol, and we're working from this isotope of manganese. So we're going to have number of protons, number of neutrons, number of electrons, atomic number. Let's see. We're using Z on. That's the atomic number. Mass number is A. That's our abbreviation. And net charge. Okay. So the number of protons. It's not up there. We have to go to the periodic table and look it up. Manganese is 25. Right? Number of neutrons would be 55 minus 25, which would be 30. Electrons. If we have an excess of 3 positives, that means that we have electrons are deficient by 3. 22. The Z number is 25, same as the protons. The A number is 25 plus 55, or 80. Right? And the net charge is 3 plus. Wait a minute. Sorry. My mistake. The mass number is given right there. Okay. Now we're correct. Yep. Nobody bothered to correct me. That's not a good sign. 46. And we have A through E. A, B, C, D, and E. Okay. FeSO4. Type 1, type 2, type 3. Well, it's a metal and a polyatomic. So it's either a type 1 or a type 2. Iron is possible multiple charge. So it's a type 2. And we have to say what the charge is. So FeSO4, we know that SO4 is 2 minus. That means 1 Fe must be 2 plus. So this is iron, 2 charge, sulfate, which is the polyatomic. Okay. Next one is NaC2H3O2. Whenever you see 3 or more elements in a formula, and one of them is oxygen, suspect a polyatomic. This is acetate, right? And the acetate has a fixed charge, sodium has a fixed charge. So all we have to do is say sodium acetate. Okay. This one, type 1 or 2. Well, silver is a transition metal, but it can only have 1 charge. So it's actually a type 1. So this is silver chloride. That's it. And the next one is CaSO4. Calcium is an alkaline earth, which has a 2 plus charge always. Remember the 2 rules for naming compounds. Unambiguous, it can only be one possibility going either direction, and non-redundant. So we don't need to say calcium 2. That would be redundant because calcium can only have a 2 plus charge. And the last one, N2O3, 2 nonmetals. This is a type 3. So we say dinitrogen, trioxide. Okay. Let's see. The next, just these 2. Write the formulas. 47. Aluminum hydroxide. Aluminum is one of those metals that has a fixed charge. So this is a type 1 compound. So when we say aluminum hydroxide, we just say aluminum, and then we balance the charge because that's a negative, that's a 3 plus. And remember, when you have a polyatomic ion, you can't change the subscript. You have to use a parentheses to get 3 negatives because that negative is distributed over the entire group. It's not localized. So you can't change the subscripts. And the last one, sulfurous acid. All right, remember, OUS ending is derived from ITE. So sulfite is that. And sulfurous acid would be 2 hydrogens. That's sulfurous acid, H2SO3. Okay, 48. The characteristic odor of pineapple is due to ethyl butanoate, a compound containing carbon, hydrogen, and oxygen. All right, there's a lot of blue smoke here. What it's asking is, if we combust 2.78 grams of this compound, it forms 6.32 grams of carbon dioxide, 2.58 grams of water. The properties of the compound suggest that the molar mass should be between 100 and 150. What's the molecular formula? All right. So the total mass is 2.78 grams. Ethyl butanoate. Okay. You don't need to know the formula for that compound. Take organic chemistry and we'll give it to you. And this is the mass of that compound before it's burned is 2.78 grams. 2.78 grams. Okay, when we combust it in pure oxygen, we get 6.32 grams of carbon dioxide. Carbon dioxide mass equals 6.32 grams. Okay. And 2.58 grams of water. Right? Now, and normally what we try to do is determine the number of moles of each element. And we know that what's left over is hydrogen, right? That mass is unknown. We're going to have to deduce that one, right? What we need to know, because this oxygen here and that oxygen there came from the combustion method. It's not part of this mass. So what we need to do is to convert this grams of CO2 into grams of carbon. Right? So what's the ratio? Well, what's the molar mass of CO2? Right? 44.01, I think. Yeah, 4401 CO2. And the mass of carbon is 12.01. So we can convert this CO2 into that carbon. And we can do the same thing for water. Right? Water is grams of water to hydrogen. Hydrogen is 1.01. Water is 18.02. Okay. Excuse me. We've got two waters in here. It's 2.02. There we go. Since we have two waters here, yeah, that's right. So this is going to be grams of hydrogen. 2.58, 2.02 divided by 18.02. That's 0.289 grams of hydrogen. And 6.32, 12.01 times that and 44.01 divided. This is 1.725. Okay, so the carbon and hydrogen together is 2.014 grams. That's carbon plus hydrogen. So what's left over is oxygen minus 2.014 equals 2.78 is 0.766 grams of oxygen. Okay. So now we have the masses for each of our elements in this compound. We can set them up and do our conversions. All right, so we've got, let's do carbon first. Carbon is 1.725 grams. Hydrogen is 0.289 grams, and oxygen is 0.766 grams. Okay. Now we can determine our empirical formula. just need to convert to moles. Carbon is 12.01. Hydrogen is 1.01. And oxygen is 16. So this gives us our mole ratio. 1.725 divided by 12.01 is 0.1436 moles. And 0.289 divided by 1.01 is 0.286 moles. This is carbon, that's hydrogen. And 0.766 divided by 16 is 0.475 moles oxygen. Now we take the smallest value and divide it into each one. Smallest one is carbon, 0.1436, 0.1436, and 0.146. All right, so of course this is going to be 1, and 0.286 divided by 0.1436 is about 2, very close to 2. 0.475 divided by 1.436, and this is 3.3. Okay, and we still have to get whole numbers. So how do we get rid of that 0.3? Well, the best way is to multiply by 3. That'll get us close to 1. So if we multiply by 3 times each one, then this one is going to be 3, this one's going to be 6, and this is going to be approximately 10. So our empirical formula is C3H6O10. No, I made a mistake. Hold on a second. Hold everything. That doesn't make any sense. I think I did a decimal place out in the wrong place. So let me check my math first. 12.01 and 1.725. That's correct. And 0.289 and 1.01 divide. That's correct. 0.766, 16 divide. Here it is. 0.0479. Okay. Now we divide by a different divisor. This is the smallest. I was off, my decimal point was off by 1. This is going to be 1. 0.286. This is going to be about 6. And .1436. Right. This is going to be 3. Okay. Now it's C3H6O. All right. So we know that the molar mass is between 100 and 150. What is the empirical weight here? Well, let's see. 12.01 times 3 plus 6.06 for the hydrogens plus 16 for the oxygen. This is about 58. Right? So if we multiply that times 2, right? If this is equal to 2, then the molecular weight would be 116, right? Yeah, 116 grams per mole. If we multiply it by 3, that'd be over 200. That's out of the range. So this is in the range. That means 2 times each one of these. C6H12O2. That's our molecular formula. All right. Let's see. Oh, 350. Got a little over an hour. Let's see how far we can get in the remaining time. $49. One of the major commercial uses of sulfuric acid is the production of phosphoric acid and calcium sulfate. Phosphoric acid is used for fertilizer. That's true. The reaction is given. What mass of concentrated H2SO4, 98% by mass, must be used to react completely with 100 grams of calcium phosphate? Okay, so we're working from this equation. Ca3PO4 2 plus 3 sulfuric acid and gives you 3 calcium sulfate and 2 phosphoric acid. That's right. Okay. All right, what are we given? Well, we're given 100 grams of calcium phosphate. Okay. And we want to know what mass of concentrated H2SO4. We want to know what mass of 98% sulfuric acid is required to be stoichiometric with this value. So remember, we can't go anywhere unless we have moles. So we got to convert this to moles. All right, 3 calciums, about 40, I think. 40.08 grams per mole. Then we have 2 phosphorus, 3097. And we have 8 oxygen. So let's see, 40.08 times 3 and 30.97 times 2. Add those together, 16 times 8. Add those together. That's 10.18 grams per mole. Now we can convert that 100 grams of calcium phosphate, 310.18 grams per mole. Find out how many moles that is. 0.3224 moles of calcium phosphate. Okay. Now we convert that to how many moles of sulfuric acid is required. In this case, what's the ratio? Calcium phosphate to sulfuric acid. We use the coefficients, 1, 3. So 3 times that is 0.9672 moles of H2SO4. All right. So we can convert this back to mass. We just need the molar mass of sulfuric acid. 2 times 1.01. Sulfur is 3207, which is only 1, 32.07, and then 4 oxygens. So let's see what that is. 32.07, 2.02, And 4 times 16 is 64. So that's 98.09 grams per mole. Now we're going to convert this to grams. 98.09 times. So this is 94.87 grams of pure sulfuric acid. Right? But this is 98% purity. So if this is pure, then what's the ratio? Well, we have 98 grams of pure H2SO4 per 100 grams of the concentrated. Okay, so that explains why I would do this. Divide that number by 0.98. That's what this does right here. And that gives me 96.81 grams of 98% H2SO4. Okay. Takes care of that one. Let's see, 50. Balance the following equation. All right. This is going to be a bear, so bear with me. Pun intended. Ki plus HNO3. Let's see, yields KNO3 plus NO plus I2 plus H2O. This particular one, we're given several reactions, and we want to use Hess's law to generate the target equation: calcium carbide plus water yields calcium hydroxide plus acetylene, and calculate the enthalpy. Okay, I can do that one. This one is messing with my mind. I need to step away from it for a little while and come back with a fresh look. So let's go to 51. If this is our target equation, calcium carbide, and the phases sometimes really matter. So let's make this one solid plus 2 water yields calcium hydroxide, right? Yeah, aqueous plus acetylene. Okay. We're going to use Hess's law. And actually, I scooted that one down too far. I guess it's all right. So if we just start down the line, calcium carbide is in the first one, but it's on the wrong side. There's the right number, 1 mole. So we need to flip that equation and put calcium carbide on this side. And the rest of the equation is calcium solid plus 2 carbon graphite. Now the value, we're going to have to change the sign on the delta H. So this is plus 62.8 kilojoules. Right? So that takes care of this one. Now, one with water in it, or, yeah, skip the second one and go to the third one. That one's got water in it. Calcium oxide plus water. Calcium oxide plus water yields calcium hydroxide. Okay, so that gives us this one on the correct side, and that's minus 653.1. Okay. And we got one water. So that's only one of these. Next, we've got acetylene. Acetylene plus half oxygen yields 2 CO2 plus water. Okay, the acetylene on that is the wrong side. It's got to go on the other side. So we got to flip that equation and put the acetylene C2H2 plus 1/2 oxygen gas. And then on this side, and by the way, we changed the sign on this one to 1300 kilojoules. And then the other side of that equation would be 2 CO2. Oops. 2 CO2 plus, and that's a gas, plus H2O liquid, right? Okay. So that takes care of the other one. So we got the waters done here and here. We got the acetylene done here, here. Now what do we have left over? Well, we've got calcium oxide, we've got carbon dioxide, we've got calcium, we've got carbon graphite. Right? So if we go to the very last one, graphite carbon is on the correct side because we have to cancel that one. So this carbon graphite plus O2 yields, oh, that's 2, right? So I'm going to write this out first. Then 2 CO2, no, 1 CO2. 1 CO2 gas. Okay. But we're going to have to double that to cancel this one. So I'm going to multiply by 2. And that means the graphite's on the correct side. The sign is correct, but we need 2 times that. Minus 393.51 times 2. So that's 2, 10, 167, 18, 167. Minus 787. That one, that one, that one, that one. And that takes care of 2 here, 2 there, and 2 there. Yeah. Okay. So we canceled this one. Oxygen, we're not going to worry about that right now. CO2, we got rid of that one. So which one haven't we used? We haven't used the first one. Calcium oxide formed from calcium. Okay, calcium is here on the right. Calcium there is on the left. That's good. So we'll make this one calcium solid plus 1/2 oxygen yields calcium oxide solid. And that takes this one out and this one out. And this half oxygen there cancels there. And let's see. Where did this one come from? I'm missing something. This one's correct. Yeah. And that's minus 635.5. Minus 635.5. We put it in as is. Right? But this one right here, I'm not sure how to get rid of that. This is calcium oxide. Yeah, calcium oxide, we got rid of that. We got the water, CO2. But that oxygen is the problem. Right? Okay, I must have made a mistake somewhere. So we have oxygen here, CO2 and water, half oxygen, and acetylene as is. Right? Yeah, so that's okay. And then the other one where we have oxygen is here. Calcium and oxygen. Half oxygen is calcium oxide. Right? I don't know where this one is. I don't know where this one goes. Right? Let me see. Had the same problem there. Yeah. So at this point, if we add all those together, we get minus 713 kilojoules, which is the expected answer. There must be something wrong with the equations that we were given, because that oxygen has to cancel somewhere. All right, we've only got a half oxygen there, and we've got half oxygen there. Oh, we got an oxygen here. That's the one that's the problem. Yep. Okay, so this is not a really good question, is it? Didn't work. All right. All right, we still got time. Let's go to 52. How many electrons in an atom can have the following quantum numbers? N equals 3. Okay. If N equals 3, and the question is, how many electrons, total electrons, can have N equals 3? Okay. So what are the possibilities for this one? Well, we can have 0, we can have 1, and we can have 2 for L. Okay? M sub L then can be 0 for this one, minus 1, 0, plus 1 for that one, minus 2, minus 1, 0, plus 1, plus 2 for that one. And then spin can either be plus a half or minus a half. So what can we get out of this? Well, we can have 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals times 2, one of these, equals 18. So you can have 18 electrons with n equals 3. Okay, and B. Let's see, B. N2L0. N2 and L0. Well, we're starting from L0, actually. So L0 is an s orbital. That's as far as you can go. M sub L has to be 0. 2 electrons each. Only 2 electrons in this case. That's it. All right. In general, ionization requires more energy from, okay, we're talking about the periodic table here. Ionization requires more energy from the bottom to the top. And ionization requires more energy, ionization energy, from left to right. Okay. So bottom to top is the first one in a family of the periodic table. Because the electrons are being removed from or added, depends on which direction you're going, that are closer to the nucleus. In other words, as you go up, you're removing electrons from more of the shell. So the outer electrons now are closer to the nucleus, and there are fewer electrons between the nucleus and the outer electrons to shield them. So you're removing shielding as you go up in the group. So which of the following has the largest first ionization energy? Well, look where sodium and rubidium are located. 54. Right? 54. Comparing sodium and rubidium. First ionization energy. Well, sodium is above rubidium. So sodium is going to take more energy to remove that first electron. And 55. Which of the following has the larger atomic radius? Okay. Remember, the radius decreases from lower left to upper right. So, and if they're in the same period, the radius decreases from left to right. Nitrogen is to the left of oxygen. So this one is going to have the larger radius. Decreases from left to right. Okay, match the ions below with the pictures that represent their relative sizes. Okay, this is going to be a challenge. Okay, we've got selenium 2 minus. Let's put these on the periodic table. Okay. So selenium, where is selenium? Selenium is 3 over and right about here. I'm just going to do the neutral atoms first. Potassium is on the same level with selenium, only it's way over here. Okay. Then gallium is right here. Okay. And bromine is right here. Oops. These are noble gases, so that's bromine. Okay. And calcium is right here. So these are all in the same period. And if we were to take the neutral atoms, we would say that the size would decrease from left to right. So we would say this one, and gallium, and selenium, bromine. Okay. Yeah, that would be the neutral atoms. But if we're going to put a charge on it, selenium 2 minus, bromine 1 minus, gallium 3 plus, yep, potassium 1 plus, and calcium 2 plus. Now we've done two things. We've subtracted, let's put the atomic numbers in here also. Potassium is 19, calcium is 20. Gallium is 31. And selenium is 34. And bromine is 35. Okay. Because the nuclear charge does make a difference. When you subtract 3 electrons from gallium and it's still got 31 protons, it's going to be the smallest. It's going to shrink way down. So gallium should be the smallest as an ion. Oops, wrong direction. This way. Which one's going to be the largest? The largest, since they're on the same level, is going to be, we're adding electrons to the same. Well, see, we're subtracting electrons here, we're adding here, right? So we're only adding 1 electron here, and we're adding 2 electrons there. So the biggest one should be selenium 2 minus, and the next one should be bromine 1 minus. Okay. Now we have potassium and calcium to deal with. All right. If we take away 2 electrons from 20 protons, that's going to be a little bit smaller. It's going to be smaller than potassium because we've taken away 2 electrons and we still have 1 more proton. So calcium should be next, and then potassium. And that's probably the best approximation to this size arrangement for the ions. 57. Okay, consider the structure of glycine. This is an amino acid. Indicate the hybridization at each nitrogen and carbon atom in the molecule. Okay. So we got this, and then we have, this is the acid part. And then this is the amine part. Right? NH2. And it's got a lone pair there. That's the only way that we can make an octet for nitrogen is by putting that lone pair right there. That's the trick. Okay. So for this carbon here and this 1 carbon, this is 1, 2, 3, which is sp2. This is sp3, 1, 2, 3, 4. This is 1, 2, 3, 4. This is also sp3. Okay. Yeah, the one that would really throw you is the nitrogen because it doesn't show the lone pair that's supposed to be there. The total number of bonds in the molecule? The total number of bonds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 bonds. Oops. Why does it say 10? Total number of bonds in the molecule. Total number of bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Should be 11. Total number of bonds. All right. If we're considering this a double bond, then okay, it would be 10. That's a technicality. Total number of pi bonds is 1. Total number. This should be the total number of single bonds or sigma bonds. That's what should be right here. So I'm going to type it in. It's easier to do that than try to find the symbol for it. Total number of sigma bonds is 10. The total number of pi bonds is 1. Okay. And 1 pi. There's your pi bond right there. Get another marker. Things just don't last. Okay. How are we doing? Oh, we're in the bonus section now. Okay. Let's see. We have a little time. 58. I think what I'll do is I'll figure out how to balance that equation and come back Thursday and present that. The period's going to be really short, so it won't take long to present this and anything that we don't get to today. So which of the following ions forms the fewest insoluble salts? The fewest insoluble salts. Okay, in this case, you got to look it up in your solubility chart. All right, so if we go to the back here and say, look at aluminum, let's see, A, B, C, D, and E. So aluminum, 3 plus. How many insoluble salts does aluminum form? Okay, I'm looking for aluminum. There it is. 1, 2, 3, 4, 5, 6, 7. It has 7 insoluble salts. Chloride. So we look for chloride and we go across. Chloride, chloride, chloride. Where's chloride? Here it is. 1, 2, 3. That's 3 insoluble salts. Nitrate. That's 0. Everything with nitrate is soluble. Hydroxide. So we find hydroxide and go across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And it's either 13 or 15. It depends on your interpretation, but that gives us a difference that we can deal with. And then magnesium 2 plus is 1, 2, 3, 4, 5. So the least is chloride. Oh, no, the least, excuse me, the least is nitrate at 0. Trick question. All right, 59. Let's see. You're holding two balloons, an orange balloon and a blue balloon. The orange balloon is filled with neon. This is filled with neon. And the blue balloon is filled with argon. I don't know about the sizes yet. The orange balloon has twice the volume of the blue balloon. All right, so this one, the volume of the neon balloon is twice the volume of the argon balloon. So this one's going to be big. Okay, and what else? The orange balloon has twice the volume. Which of the following best represents the mass ratio? Okay. If these are, this is twice the volume of that one, that means the number of particles of neon, the moles of neon, are twice the moles of argon. Okay. So what's the molar mass of argon? Argon is about 40 grams per mole. And neon is about 20. Okay. Now, neon to argon ratio by mass. Mass. If they were exactly the same number of particles, then the mass ratio would be 1 to 2. Excuse me, would be, hold on a second. If they're the same number of particles, yeah, it'd be 1 to 2. You'd have twice as many particles here as you do there. Now that'd be 1 to 1. But the number of moles here is twice the number of moles there. Okay, if we have twice the number of moles here, that means 40 grams. If this is 2 times and this is 1 times 40, so the mass ratio should be 1 to 1. Yeah. If we have twice as many here, twice as many moles here as here, then we multiply that times 2 and we get 40 grams. So the ratio is 1 to 1 by mass. $60. Which of the following electron configurations is different from that expected? All right. B, C, D, E. Okay, the first one is calcium, then scandium, titanium, vanadium, and chromium. All right. So calcium is going to be argon and 4s2. There's nothing unusual about that. Scandium is going to be argon, 4s2, and then 3d1. There's nothing unusual about that one either. Titanium is next to scandium. So it's 4s2 and 3d2. There's nothing unusual there. Vanadium is, keep going, right next door, S2 and 3d3. Okay, nothing unusual there. Chromium is 18 argon, 4s2, and 3d4 is our first estimate. But remember, when you get close to, right, you have 5 D subshells. So if we put 4 like that, it would prefer to be 5, half filled, D, is more stable. And if we take one of these and put it over here, then we get that one half and that one half. And what that does is it makes these happy by one in each subshell, and it removes that one here that's repelling the other one. So it's a win-win. This is the one that's unusual, E. All right. 61. Choose the molecule with the strongest bond. Well, let's see. A, B, C, D, and E. So what do we have? We have methane. We have H2O. We have NH3. We have HF. And equal. All equal. All right. These are all covalent compounds. So what we need is to look at the bonds, right? What kind of bond do we have here? Well, they're all single bonds, for one thing. And carbon and hydrogen are fairly close in electronegativities. That's probably not it. Oxygen is like this, single bonds, but the electronegativity difference is a lot greater. So these bonds are stronger than these bonds. And then ammonia is like this here, here. And actually, this is stronger than that, and this is stronger than that, based on electronegativities. And this is a single bond here. And the electronegativity difference between hydrogen and fluorine is not only greater than any of the others, what we have is the ability for this hydrogen to get very close to the fluorine, and this hydrogen is essentially a proton. No, it's based upon electronegativities. Right. That gives you the strongest bond. The difference in electronegativities, that's where we're going with this problem. So HF is the strongest. All right. How about 62? We got 10 minutes. Which of the following species has the largest dissociation energies? In other words, the largest amount of energy we have to put in to break the bonds. Okay, if we, what we're looking for is the bond order, the strongest bond. The weakest bond, the strongest bond, excuse me, will have the largest dissociation energy. So we got O2, O2 minus, O2 2 minus, O2 plus, and O2 2 plus. Now this dioxygen has no mixing. So we've got how many electrons with this one? Valence electrons is 12 electrons. So we're going to have sigma and sigma star from the 2s. Then we're going to have sigma from the 2p and pi from the 2p, and then pi star from the 2p and sigma star from the 2p. So 12 would be 2, 4, 6, 10, 12. Okay. And the bond order we know is going to be 2. What happens when you add an electron here? You're adding an electron to an anti-bonding orbital because you've got room for 2 more here. When you do that, you reduce this one by 1/2. When you add 2 more, you reduce it further by 1/2. Okay? When we subtract 1, we're subtracting 1 from an anti-bonding. So we increase it by 1/2. And if we go 2 plus, then we're subtracting from an anti-bonding and we go to a 3. Bond order. Okay. So the largest dissociation energy is the one with the largest bond order. That one right there. So that we could interpret that as a triple bond. All right.